Hey guys, so I wanted to go through the derivation for the moment of inertia of a hollow cylinder. We started this in class, but we weren't going in the right direction. I knew there was something I was missing. So I wanted to put it on paper. We can go over it in class, but you'll have this to reference back to. So essentially we're looking at a cylinder. These are the sides of it. So it kind of goes back like this. Yeah. All right, so I do it poorly. I was drawing it out though, so it has an inner. So the green, that's the actual wall of the cylinder. I'll talk about that yellow in just a second. And so basically, what we're going to do is we're going to define a radius here to the inner wall, and that's going to be little r. And then we'll define a new radius all the way outside, and that's big R. And so what we're going to do is we're going to take a little slice of the entire cylinder, and that's this little area right in here. So this little piece. And then what I'm going to do is I'm going to draw it down here like I did in class. So we're going to, because it's a little easier to think about. So I'm taking that little sliver out and flattening it out. So basically I cut it and I unrolled it. Now, what we're looking at is, or what we need is this little distance right here. And that little distance is just a little piece of R. So we can call that dr. That's a piece of the big R. So it's a little tiny piece of that. Okay, so that's going to end up, since that's the width of this thing, that's going to end up being the height here. So that's going to be dr. In class, this is where we messed up. We had put like r minus r, but that will pop back out. We'll see those difference. And then the length of this thing is going to be the circumference. So it's going to be 2 pi. And you know what? I'm gonna say little r here because we're close to this. It doesn't matter. You'll see. And in fact, you know what? We can change that to a little r as well. Don't get confused with these r's. So let's change that to a little r. So it's a little piece of the radius. Okay, so looking at this picture, we can now see some things. Remember that this is flattened out, so there is a length here, and so we can get the volume. So the volume of this thing is going to be 2 pi r, the length here, times this length, times L, times dr. And then it's a uniform density, so the density times the volume is equal to the mass, and this is a little piece of the volume. So a little piece of the mass is a little piece of the volume times the density. So what we'll have is we'll end up doing, we'll do our substitution as we did before. So the inertia of this thing is going to be the integral from little r to big R of r squared dm. So that's just our definition. And then what we're going to do is we're going to change this dm. So I'll write what I'm going to substitute over here. So dm is equal to the density times the little piece of volume. And the little piece of volume, we said, is this right here. So it's 2 pi r L dr. So we'll substitute all this in for dm. So we get the integral from r, little r to big R of r squared times rho 2 pi r L dr. Okay, don't be scared. Most of the stuff is constant. So let's go ahead and pull out all the constants just so it's easier to see. And so density is constant, 2 pi. The r is going to go with this one, so the length. So we'll pull all that stuff out. So we get 2 pi density times length times the integral of r, big R, and then we have an r squared times an r, so we end up with r cubed, and that's dr. And now it's pretty clean, so now we can integrate. So we're going to end up with 2 pi rho L times It's going to be 1/4 r to the 4th integrated from little r to big R. So we get 2 pi rho L times 1/4 big R squared minus 1/4 little r squared. And then we're going to do some algebra trickery with this stuff. So 1/4, if I pull that, it's common to both of them, so let's factor it out. And 2 over 1/4 is 1/2. So we get 1/2 pi rho L times r squared. I'm sorry, this is r to the 4th. I messed up there. Sorry about that. R to the 4th minus little r to the 4th. Okay. So here, r to the 4th, r to the 4th, that's the same. Let me switch colors. That's just big R squared squared minus little r squared squared. So what we have is we have a difference of squares. So we can rewrite that. That's going to be 1/2 pi rho L times big R squared minus little r squared times big R squared plus little r squared. So that comes from our difference of squares. We can rewrite it like this, and you can check that with distributive property. So we're going to have to switch everything over to mass, and remember that mass is, the entire mass is density times volume. So we want to get the volume of this thing. And so the volume is, I want to scroll down just a little bit. The volume is area times length. So we need to get the area of this face, and then we would just multiply by length. So the area is going to be the area on the outside minus this area that's missing. So the area of the outside, well, that would be pi big R squared, pi big R squared minus the area of the inside, which is pi little r squared, pi little r, oops, that's not squared, pi little r squared, and all of that times length. Okay, so now you can see, you might be able to see what's going to happen. We're going to substitute over here. So I have pi's in common, so I get pi, and then I'll move L to this other side. So times L times, I factored out the pi, so I get r squared minus little r squared. So that's my volume. And then if I get the mass, it's just density times all of that. So I can see that the mass is going to be rho times all of this stuff. So rho times pi times L times r squared minus. So all of this stuff, that's all the volume. So we get, I'm sorry, that's the mass. So we get 1/2 of the mass times r squared plus r squared. This equation here, this is the inertia for a thick wall. For a thick wall. A lot of times they write it as a squared and b squared, but it's the inner radius and the outer radius. But what if it's a thin wall? Well, if it's a thin wall, then r basically equals little r equals big R. And so we get 1/2 m, and then it's going to be big R squared plus big R squared, so we get 2 big R squareds. And 1/2 of 2 is 1, so we get mr squared, QED. So there's your derivation. There's a couple little tricks in there. So just practice this. Do this one, make sure you know this one, and the rod. Know the derivations for both of those.